Hey guys, today we're kicking off chapter 6. On this unit, you're going to see on the assignment sheet how small it is. We've actually covered quite a bit of this stuff already. It's just kind of giving it some formal names. So even though you had to learn all that new stuff in Unit 5, I feel like Unit 6 is going to be a little bit of a breather for you. This first day, so we split 6-1 into a couple parts. And today we're just looking at day 1. We're looking at solutions of diffie-qs, differential equations. We've talked about these already. A differential equation is just something that has a derivative in it. So if we're thinking of, let's think of something. What about this one? Right? Here's a function that has a derivative in it. And then a question sometimes would say, we'll find the general solution. So we would say, what function has this guy as a derivative? And we know that it would be this function right here. And if you remember, this is called the general solution. Okay, so here's an example of a differential equation right here. That's a differential equation. Another one, maybe it looks a little differently. Maybe you have something like this, dy dx equals 3x. Okay, so a differential equation, again, just has a derivative in it. We've been doing this for a very long time. The order, so this part that's coming up next, it says the order of a diffie-q is the highest derivative present in the equation. So if we had something, let's use a different color. What if we have this? So we learned this back in semester 1. If you take the second derivative, let's say this is 4x. So it doesn't really matter that it's 4x. We care that it's looking at the second derivative, and this is called the second order derivative. This first one that we looked at over here, this is a first order derivative. It has nothing to do with this and everything to do with the fact that it's the first derivative. Okay, so just recapping what we did to go from 2x to x squared. So we took this differential equation and we found the general solution. We know that anti-differentiation, indefinite integration, all of this means the same thing. And now we're going to be looking at solving differential equations. That's the same thing as finding the antiderivative. So just taking the derivative and saying, what function did this come from? The ones that we've looked at so far, if you look at, they're calling them explicit functions because look at dy dx and we have all x's, all t's. Okay, so what we had to do here is we had to integrate to get back to the original. This is all kind of saying the same thing. The one I did up here was the general solution. Remember, sometimes we could find the particular solution also, and that meant they're going to give us an ordered pair for x and y, and then we're able to find c. Okay, a separable differential equation is one in where all x's and dx's go on one side, and then y's and dy's go on the other side. So it would look something like, we would have an f of y dy on one side, so a function with y's, and then a function with x and dx on the other side. Notice that I used a lowercase f. So if these are differential equations and we want to get back to the original function, what we're going to be able to do is we're going to be able to integrate both sides, and then in doing so, we'll find out what the function was originally before the derivative. Okay, separable, and again, we're going to explore a lot of this throughout this unit. So a separable just means y's and dy on one side, x dx on the other. Okay, we already talked about first order separable differential equations, and then I'm going to go through some examples. It's really important, again, it's all caps, show separation of variables. These problems are going to come up on the FRQ quite often. Of the 6 problems, one of them has to deal with these, and as we go through the unit, I'll show you how College Board applies this to the AP test. Okay, these directions, I tried to match them with the text. So the problems aren't hard in and of themselves, but sometimes you might get tripped up on the directions. So if you're struggling with anything in the book, look back at the notes and see if you can find something similar. Notice this is a verify, so it has to work out. So we're jumping right into example 1. Again, guys, if you're thinking like, hey, we've done this stuff before, a lot of it we have. Okay, it's just going to be presented in a different fashion. So they give us this equation, y squared minus 2 ln y equals x squared, and they're saying verify that that's a solution to this differential equation, right? Before we've just probably called this the derivative. It's a differential equation. So what we need to do, notice that this has a dy dx in it here. So we're going to apply the operator d dx to both sides, take the derivatives of both sides with respect to x. Okay, let's go ahead and do this. So the derivative of y squared with respect to x, this is implicit. So this is using stuff again from unit 1. It's going to be 2y prime minus 2. And then if you guys remember the rule for natural log of y, you take whatever the natural log of, and that goes on the bottom, and the derivative of the bottom goes up top. And then the derivative of x squared, that's just a neat 2x. Now remember our goal here, you're trying to verify that the equation they gave you is a solution to this differential. So notice they have dy dx on one side. This is the same as dy dx, so we're going to go ahead and solve for dy dx. We can't combine terms, so we're going to factor out a y prime. And we're going to get 2y minus 2 over y equals 2x. Okay, at this point, we can go ahead and isolate dy dx, which is y prime, by dividing both sides by 2y minus 2 over y. And if you saw everything has a 2 in it, we could have also factored that 2 out. Okay, in the next step, we can't have 2 over y in the denominator here, so let's get rid of that by multiplying at both top and bottom, so numerator and denominator, by y. So that's going to give us 2xy over 2y squared minus 2. We're almost there. Again, our goal is, they said it has to work because it said verify. It didn't say will it work. So we have to keep simplifying until we get here. Again, the only thing it looks like out of place now is, let's make sure we wrote dy dx if they have it. And then also they have a 2. We can divide everything by 2, and now we have the right answer. Verify? Sure, we're good. Okay, so when you see questions like that, that's what they're asking for. Now this one, it's similar, but they didn't say verify. They said determine whether y equals 2x is a solution to the diff EQ. Remember that this right here, because it's in parentheses, this means the fourth derivative. So again, what this question is saying is if I have this function, and if I take the fourth derivative of that function minus 16 times the function, will I get 0? So it's saying, is this a solution? So we have to figure it out. So let's start with what they have, 2 sine x. We're trying to find all the pieces. So see how they have a y here? We can replace this y with 2 sine x. What we don't know is what to replace the fourth derivative with yet. So we have to find out what that is. So the first derivative is 2 cosine x. The second derivative, remember the derivative of cosine is negative sine, so we're going to get negative 2 sine x. The third derivative, the derivative sine is a positive cosine, so we're going to get negative 2 cosine x. And then the fourth derivative, we're sick of writing those tick marks, so this is standard practice. And then the derivative of cosine is negative sine, so we get 2 sine. Now the question is, if I take the fourth derivative, which is right here, if I minus 16 times the original function, will I get 0? Let's not write it equals 0 right away because we don't know if it does. We're trying to prove it. So the fourth derivative, let me write this out just so you can see exactly what I'm doing. The fourth derivative is 2 sine x minus 16. So again, I got the fourth derivative from right here, minus 16 times y, and I'm going to replace y with 2 sine x. Remember, our goal is when we did this to get 0, let's see if it works. So now we have 2 sine x minus 32 sine x. That is going to be negative 30 sine x. And what did they claim? They claimed that we should get 0. Did we get 0? No way. That's not equal to 0. Because that is not equal to 0, we would say y equals 2 sine x is not a solution of the fourth derivative minus 16, what we started with, equals 0. Now, there probably is a function out there such that when you take its fourth derivative minus 16 of the original, you get 0. It's just not this guy. So they said determine if it's a solution. We said it's not a solution. Okay, just 2 more. Going on to this one, verify the particular solution. So we have this solution right here of the diff EQ. Here's our derivative. They wrote y prime instead of dy dx. So they're saying verify again. That means it has to work. So this is like example 1. This is saying the derivative should be what I started with, which is my y, times sine x. We have to verify it. So let's go ahead and do that. The derivative, I'm going to take this function right here. And the derivative of this, if you guys remember, if you have e to a power, you copy that over, and then you take the derivative of the exponent. The derivative of cosine is negative sine, so the derivative of negative cosine is going to be positive sine. So we took the derivative, and then we'll stop for a second and say, what were we trying to do? We were trying to verify, so we know it has to work, that when I take, that the derivative is equal to what I started with times sine. So the derivative, notice the derivative, should be what I started with times sine. Well, here's sine. Can I replace this with something? Sure. What's e to the negative cosine x? Isn't that y? And that's what I'm trying to get to. So over here I can say e to the negative cosine x. Instead of writing that, it's the same as y. So I'm going to get y sine x, which is exactly what they claimed. Let me go over that part again. Again, all we're trying to do is show that the derivative is y times sine. So first I have to find the derivative. I found the derivative right here, but I'm trying to match this with this. They both have sines, but this has a y, but then if you notice, this can be replaced by y. So yes, I've proven what I need to. Now, some of the problems, maybe 29 and 31, ask for something just super basic. It's also saying verify that if I sub a pi over 2 into y, I get 1 out. Well, this is talking about y. What function is talking about y? This function right here. So all we have to do is sub a pi over 2 in for x, and do we get 1 out? So let's go ahead and check that. Y of pi over 2. Again, what you have to look for is there's two functions, y and y prime. This is talking about y. So y of pi over 2 is going to be e to negative cosine of pi over 2. Well, what's cosine of pi over 2? Unit circle, here's pi over 2. Cosine is the x value, which is 0. And e to the 0 is 1. And what did they claim? They claimed when you sub a pi over 2 and you should get 1. And we did. We're good. So we verified the particular solution of the diffie-q, and we confirmed this value. Okay, last one. Verify the general solution. So going back up here, particular solution. Look, they said particular solution. Do you guys get there's no c? There's no plus c. Now they're saying general solution, and do you see there's a plus c? Okay, so we have to verify, again, it has to work that it satisfies the diffie-q. This diffie-q is a little more complicated. This one was a little more straightforward. Then we have to find the particular solution. Finding the particular solution means finding C1 and C2, and look at, they gave us two ordered pairs. So let's do this, the first part. Let's go ahead and verify the general solution satisfies the diffie-q. So let's do this first. So what we do always is we look over here at the diffie-q. Look at it has the second derivative in it. So I need to find the first derivative, sub it in here, the second derivative, sub it in here, multiply by x, and when I simplify this, I better get 0. And I say better because they said verify. It didn't say will it work. Okay, so let's go over here and find the derivative. The derivative of c1, because that's a constant, is 0. The next derivative, c2 is a scalar, and the derivative natural log of x, because it's just x, is over x. Now I need to find the second derivative, the reason being because this has a y double prime. So what I'm going to do is rewrite this to be calculus friendly and then erase what I just wrote because I meant to write y double prime and take that derivative, which is negative c2 x to the negative 2, which is negative c2 over x squared. So again, we're still trying to verify the general is a solution to the diffie-q. The diffie-q is right here. It's x. Replace y double prime with negative c2 over x plus, and then replace this y prime with c2 over x. Now, remember when you've done math before, if you're trying to verify something, you don't claim it as right off the bat. That's not proving anything. We want to clean this up to show that we get equal 0. So now I have negative c2. Oh, did you guys notice there's a mistake here? Look at when I subbed y double prime in. Do you see it's supposed to be negative c2 over x squared? I forgot to write the squared. So negative c2 over x plus c2 over x, well, what's that? That's clearly 0. So what we just did is we verified that the general solution right here satisfies the differential equation because it all simplified and we got 0 like we were supposed to. Okay, so we're good there. Now look at this next part. It says, then find the particular solution that satisfies the initial condition. So this is using 2, 0. Y equals 0 when x equals 2. They're talking about y, so this is like the ordered pair x, y. So find the equation that has an x, y in it, which is right here. Go ahead and replace this x with 2 and this y with 0. So you get 0 equals c1 plus c2 ln 2. That's going nowhere fast. I mean, we have two variables, c1 and c2, and we don't know. And we just have one equation. We can write it a little nicer and maybe add the negative c2 ln 2 to the other side, but then we're still stuck. But lucky for us, they gave us another ordered pair. Look, they said 2½ but that's for y prime. So what equation has y prime in it? Here's y prime. It's c2 over x. So we're going to replace y prime with a half and x with a 2. So we're going to replace y prime with a half and x with 2. So c2 over 2. Again, it was y prime with a half, c2 over x, but x was 2. Now, just looking at this, I mean, I don't know if you want to cross multiply, but like the 2 matches, c2 has to be 1. Okay, if you cross multiply, you'll get the same thing. So c2 is 1. Now, we were trying to find the particular solution. The particular solution replaces c1 and c2 with numbers. We have c2 with a number, but we have to find c1. Well, here's the rule for c1. So let's go back over there now, and let's say c1 is now going to equal negative c2, but c2 is just 1, so negative ln 2. So now, if we write our particular solution, you don't have to copy this over. I'm just doing it to show you how things match. Look, here's our original one here. We're replacing c1 and c2 with what we just found them to be. So c1 we can replace with negative natural log of 2. We can replace c2 with 1 and just get natural log of x. Now, that's fine if we want to clean it up. Simplifying natural logs, you're going to get natural log of x over 2. Okie doke, that's it. See you guys later.